Welcome back to my YouTube channel Analytical Instrumentation with Bhumika Sharma. Today we will learn about the basics of infrared spectroscopy. IR radiation spans from wavelength 0.78 to 1000 micrometer and or wave number 13,000 to 10 centimeter inverse. Wave number is basically the number of waves per unit length and it is the reciprocal of wavelength. So wave numbers is the IR spectra is mostly presented in the wave numbers. So why is that so? Wave numbers is the inverse of wavelength, and as you can see here, E is equals to h nu and E is equals to hc over lambda. So the relation of wavelength to the frequency and energy is inverse. To make our calculations easier, we use wave number that is directly proportional to the frequency as well as the energy. The IR region is divided into three, that are near IR, mid IR and far IR. So the far IR region requires specialized optical materials and sources, whereas the near IR region is due to the overtones or combination bands that we will discuss later. These are the forbidden transitions. So the most frequently used IR region is mid IR region. The mid-IR region has three important regions, that are functional group region, in which the functional group is determined, fingerprint region, uh, and the aromatic region. So the wave numbers for functional group region are 4000 to 1300, fingerprint region 1300 to 900, and aromatic region 900 to 650. Infrared spectroscopy is also an absorption spectroscopy. Similar to UV visible spectroscopy, it follows Boger-Lambert-Beer law, which states that absorbance is directly proportional to the path length as well as the concentration of the sample. Where capital A is the absorbance, small a is molecular uh, absorptivity, and molecular absorptivity is given as epsilon. I have already discussed the difference between A and epsilon in my previous videos, so you can go through them. B is the path length and C is the concentration of the sample. So the intensity of absorption bands are directly proportional to the concentration as well as the path length. Deviation from Beer's law in infrared spectroscopy is similar to that of UV visible spectroscopy, but the deviation occur more often in infrared spectroscopy. So I have already discussed about the deviation. They are of two types: chemical deviations and instrumental deviations. Instrumental deviation is due to stray radiation, insufficient resolution, and chemical deviation is due to molecular interactions, such as hydrogen bonding, and molecular association or dissociation. Process of IR absorption and molecular vibration. To absorb IR, the molecule must have a dipole moment. So what happens is the molecules get excited when they absorb IR radiation, and it will move to the from the ground energy state, it will move to the higher energy state. HOMO and LUMO I have already discussed. So it is also a quantized process as absorption is involved in it. Absorption process is involved, and these frequencies led to the change in energy on the order of 8 to 40 kg per mole. And this energy change will lead to the vibrational frequencies of the bonds, and the vibrational movements, molecular vibrations can be stretching or bending.
When a molecule absorbs IR radiation, these radiations are converted into various types of motion. Mainly, these motions are because of these absorbed radiations. So, these motions are known as molecular vibrations. Molecular vibrations are classified into two: stretching vibrations and bending vibrations. So first we will discuss about the stretching vibration. Consider this as your complete molecule, these pen caps as the atoms, and these as the bonds between the atoms. So, stretching vibration is of two types: symmetric stretching and asymmetric stretching. In symmetric stretching, the direction of motion will be same. In asymmetric stretching, the direction of motion would be different for different bonds. Okay, so here you can see that in stretching vibrations, the bond angle remains the same, but bond length varies. Now, talking about bending vibration are of four types. First, we will discuss about rocking vibration. In rocking vibration, the molecules will experience this type of motion, right? This will move like this and this like this. Okay. Now scissoring. Scissoring motion will be same like the scissors. Now wagging. In wagging, the plane will change, but both the molecules will move in the same plane like this. And in twisting, the plane will change, but the molecules will move in different planes like this.
But the bond length varies. Whereas in bending vibrations, the bond angle varies, but the bond length will remain the same. Bond properties and absorption trends. The frequency of a bond is given by Hooke's law, according to which frequency is directly proportional to the force constant, or you can say the bond strength, and inversely proportional to the reduced mass. So here 1 upon 2 pi c under root k by mu, where mu nu is the frequency, c is the velocity of light, k is the force constant or the bond strength, and mu is the reduced mass that is given by the formula m1 plus m1 into m2 upon m1 plus m2. This is given in terms of grams. To convert it into atomic unit, we multiply Avogadro number. Simplification of Hooke's law, as I have already told you that the Avogadro number is multiplied, so it is given like this in the numerator. It is converted into the numerator form by calculations, and we put the values of pi and c. So now the simplified equation is 4.12 under root k by mu. As you can see here, that mu is inversely related to the frequency. So the heavier the atoms, the more will be the reduced mass and the lesser will be the frequency of that particular molecule. And K is the force constant or the bond strength. The values for force constant for different types of bonds are: for single bond it is 5 into 10 to the power 5. For double bond, it is 10 into 10 to the power 5. And for triple bond, it is 15 into 10 to the power 5. So, when the bond strength increases, the frequency also increases. So, by using this formula, we can estimate the K. We know the K of the molecule depending upon the molecular structure. We know the mu of the molecule, so we can calculate the frequency. So types of IR bands: fundamental absorption band, in which the molecule from its ground state get excited to the higher energy level state, right? So from HOMO to LUMO, highest occupied molecular orbital to lowest unoccupied molecular orbital. This is the fundamental absorption. In overtone bands, the molecule will get excited from the ground state to the higher energy state like this, right? In combination bands, two vibration frequency combine to form a new frequency, whereas in difference bands, two vibrational frequency, there is a difference between two vibrational frequencies and new frequency is generated. In Fermi resonance, fundamental vibration is combined, or it couples with the overtone or the combination band. So these are the different types of IR bands: fundamental, overtone, combination, difference, and Fermi resonance. IR spectrum. In IR spectrum, wave number is represented on the x-axis, whereas the percentage transmittance is represented on the y-axis. Mainly, the y-axis can be absorption intensity as well, but we prefer transmittance because it provides better contrast between strong or weak bands, between the intensity of strong or weak bands, because transmittance ranges from 0 to 100%, whereas absorbance ranges from infinity to 0. This is an infrared spectrum, in which here you can see on the x-axis there is wave number in centimeter inverse, and on the y-axis there is transmittance, and these are the bands. Now why these are represented as bands and not peaks? I have already discussed about the different energy levels that are electronic, vibrational, and rotational. In UV visible spectroscopy, I have discussed about it. So when a molecule absorbs infrared radiation, so there will be involvement of vibration as well as rotation. That is why the spectrum is shown as peaks and not band. The spectrum will be in the band form and not the peaks, not particular peaks are shown due to the involvement of vibrational as well as rotational energy levels. The table given here shows the different groups, their molecular vibrations and frequencies. And this table shows the vibration and molecular frequencies of ether, aldehyde, ketone, etc. These are the references. Thank you. For any queries or suggestions, you may comment in the comment box.